My undergraduate studies in biopolymer nanogenesis water remediation. My name is Richard Park, Department of Polymer Nanogenesis Material, and I would like to introduce my supervisor, Associate Professor Manny, and the reviewer, Master of Science from UCAM. My presentation includes four main parts: introduction and background, experiments, result discussion, and finally conclusion. Now we will go to the introduction and background, the motivation behind one of the design. Nowadays, the fast expansion of transportation and industry has provided normal convenience. However, it's also led to accidents and the release of oil contaminant into the environment. So they contaminate and destroy the ecosystem and endanger human health. Various solutions have been active for remove oil and water, including burning oil in situ, using manual labor, physical collecting, or using chemical dispersants. However, there's still some limitation of this method, such as low performance, inflexibility, and high operational cost. On the other way, using certain material offer a convenient and eco-friendly solution. This is widely recognized as the best method for only water treatment. Currently, polypropylene parts are used for controlling oil spills. However, this material is single-use and non-reusable. So, this drawback motivates my research to design a new reuse form, design a new super material, that's develop a better super material. So, compared to the polypropylene parts, flexible polyurethane sponge is easily synthesized by condensation reaction of the boron and steel group. This material displays outstanding properties for solvent material, including porous three-dimensional structure, give it a high absorption capacity, flexibility in various conditions, and reapplication ability thanks to its good elasticity. However, the commercial we use derive entirely from petroleum, hydrophilic characteristics, and functions as a non-selective solvent for oil and water. So this drawback making it low efficiency in application. Therefore, my objective is to design a new reuse form that enhance the oil absorption efficiency while reduce the reliance on petroleum in polymer reduction, promoting sustainable development. After some research, I found a few foundations necessary for achieve my goal. Firstly, bamboo is easy to run while it is distributed and rapidly renewable land. Especially bamboo is rich in aliphatic and aromatic amino group for reducing boron. So this bio-boron can replace the petroleum boron in biomass polyurethane synthesized, promoting sustainable development. Next, the iron oxide nanoparticle with their nano size can increase the material surface roughness, while the stearic acid with the long non-polar chain can reduce the surface energy. Especially, these substances are eco-friendly and interact very well with each other to create a durable hydrophobic coating. So, this coating can enhance the oil absorption efficiency of the BBU store. From the background just summarized, I would like to introduce my research, biopolyurethane nanocomposites, synthesized evaluation of physical chemical properties for water remediation. My work involves synthesize the biomass reuse form, then modify it with iron oxide nanoparticles and stearic acid to obtain the durable hydrophobic BBU nanocomposites for oil water treatment. To be specific, we're going to go to the experiment session. The experiment session includes three main steps: synthesize the biomass reuse form, synthesize the magnetite nanoparticles, and fabrication of the hydrophobic BBU nanocomposites. The first step is design the BBU. Boron is a key ingredient for BBU design. In this work, bamboo boron will convert it into the liquid boron using the microwave. With the sulfuric acid and the catalyst, polyethylene become glycerol at the liquefaction region. Next, the obtained bioboron will mix with catalyst for 3 minutes. Then the isocyanate will add before and mix in 30 seconds before being allowed dry release to obtain the biomass PU material. Finally, cutting the material to 1 centimeter and treat with acetone to obtain the crystal BBU sponge. In the second step, the magnetite nanoparticle were synthesized using the co-precipitation method. First, the iron 2 chloride and iron 3 chloride solution were mixed to get the uniform solution. Next, the sodium hydroxide were slowly dripped into the mixture. The reaction system will maintain at 70 degrees Celsius for an hour under strong magnetic stirring to form the chemical precipitation. Next, the precipitate were separated and washed with distilled water and ethanol. Finally, they are vacuum dried at 70 degrees Celsius and masticated to obtain the iodine nanoparticle. The final step is combine all the components using the deep coating method. Firstly, the iodine nanoparticle suspensions and the stearic acid solution were repaired using ethanol and solvents. Some of the BBU were suffocated in the suspension for 50 minutes at room temperature, then drying at 60 degrees to obtain the BBU magnetite. Next, the magnetite BBU were shocked in the SA solution for 4 hours at room temperature, finally drying at 80 degrees Celsius to obtain the durable hydrophobic BBU nanocomposite. The next step is the evaluation of the obtained product. In the results discussion session, we discussed about the structure and morphology of the magnetite nanoparticles and the properties of the BBU of the crystal BBU and the hydrophobic BBU nanocomposite. I use X-ray diffraction and field emission scanning electron microscope to analyze the structure and morphology of the magnetite. In figure 3.1a, the XRD pattern reveals 6 typical diffraction peaks corresponding to the crystal plane of the cubic magnetite, indicating that the iron oxide have inverse linear cubic structure. In figure with the scale of 100 nanometer, the morphology of the iron oxide is high agglomeration of the multiple sets, including the spheres ranging from diameter ranging from 12 to 23 nanometer, and the rocks around 20 to 40 nanometer wide and 80 to 200 nanometer long. So this result indicate us the iron oxide have been successfully synthesized by the co-precipitation method, resulting in nano-size particles. Next, we discussed about the structure and morphology of the crystal BBU, the BBU nanoprocess. SDM images were used to analyze the structure of Zucchius sponge. Figure 3.1a show the three-dimensional color network of two samples. This structure very important for storing the oil contaminant. In figure A1, with the magnifier at 100 nano, 100 times, the BBU shows us smooth skeletal surface. After modification, the BBU nanocomposites are forming a round surface after the coating hydrophobic layers. While they are maintaining the polymer pores, this structure can enhance the water repellency and oleophilicity of the material. When surveying describe the interaction between water and the material. In figure 3.3a, two gas samples were put on the water surface. After 5 minutes, the reservoir is having its hydrophilic character and somewhat below the surface, while the nanocomposites remain floating. In figure B and C, the vector meters were further investigated using the water droplets. In the BBU form, the droplets rest with the water contact angle in 64. In contrast, the droplets remain stable on the BBU nanocomposites with the water contact angle in 144, indicating that the nanocomposite have the strong hydrophobicity. I use the rescue test to study the mechanical properties of the polymer. The Schwarzschild curve is hiding the three distinct regions of the two gas samples, including the linear inlet region, the core collapse region, and the gasification region. So this region is hiding the characteristic of the elastomeric polymers. Their elasticity is very essential for the application. In applicating the nanocomposites, the assumption capacity and the usability were using the weighting methods with the hexane, gasoline, cooking oil, and diesel, and the test systems. In figure 3.5, the assumption capacity also ranging about 9 to over 15 gram per gram of the sample waste. With the highest capacity for diesel and the lowest for the hexane. There are a significant drop after the first cycle due to the high enhancement viscosity of the residual oil. In the next 9 cycle, the assumption capacity stayed around 80% at the first cycle, with around 10% fluctuation. So this movie demonstrated an efficiency in oil pollution remediation of the nanocomposites compared to the recent BBU form. So, in conclusion, this result of the study demonstrate my successful synthesizer flexible biomass used from bamboo and magnetized with the nanoside particles. I also successfully nanocomposite solvent for selective oil removal. They are strong hydrophobicity with the water contact enjoy 144. Absorption capacity is exceeding 50 times its weight and reusability for 10 cycles, maintaining 80% efficiency. However, maybe my research is a few limitations. So I have a few recommendations to improve and further expand this study area. For improvement, I recommend enhancing electricity for more efficiency reuse and raising the waste limit to super hydrophobicity to increase the treatment efficiency. For further research, I recommend enhancing the plant vitality to ensure the fire safety and diversity of the process in Bolivia synthesize for sustainable development and environmental protection. After I participated in lab over 2 years this year, I have attended with achievements for the extra credits, including 2.25 extra credits. So at this time, I would like to conclude my presentation. Thank you so much, and I will come to questions.